Have you ever wondered what the universe is made of? Scientists have been trying to answer this question for centuries, but the more we learn, the more complicated the answer becomes. One theory that's gained a lot of attention in recent years is string theory. At its most basic level, string theory suggests that everything in the universe, from stars and planets to particles and forces, is made up of tiny strings that vibrate at different frequencies. Why is this important? Well, if string theory is true, it could provide a way to unify all the fundamental forces in nature, something that traditional physics has struggled to achieve. It could also help us understand some of the biggest mysteries in the universe, like the nature of black holes and the Big Bang. But as you might imagine, string theory is a complex and highly theoretical concept. It requires a deep understanding of mathematics and physics, and even then, it's not yet fully understood. In this video, we'll do our best to explain string theory in a way that's easy to understand, even if you're not a physicist. We'll start by going over the basics of how string theory works, and we'll explore some of its implications and challenges. Finally, we'll look at where string theory is headed in the future, and what it might mean for the future of science. So whether you're a science enthusiast, or just curious about the universe, let's dive into string theory and see what all this fuss is about. String theory has had a long and complex history, dating back to the early 20th century. It all started with the development of quantum mechanics, a revolutionary theory that described the behavior of particles at the smallest scales. However, there was one major problem. Quantum mechanics and general relativity, Einstein's theory of gravity, were fundamentally incompatible. In the 1960s, a breakthrough occurred when a group of scientists discovered that particles could be described as tiny strings instead of point-like objects. This was the birth of string theory as we know it today. Over the following decades, physicists worked to further develop the theory, exploring its mathematical and theoretical implications. They discovered that string theory could potentially unify all the fundamental forces of nature, providing a way to reconcile quantum mechanics and general relativity. However, progress in string theory has not been without its challenges. One of its biggest obstacles has been the lack of experimental evidence to support the theory. Since strings are so tiny, on the order of 10 to the negative 33 centimeters, it's incredibly difficult to observe them directly. Despite these challenges, string theory remains one of the most exciting and promising areas of physics today. Researchers continue to work on developing the theory and exploring its implications, in the hopes of one day unlocking the secrets of the universe. In summary, string theory has a long and fascinating history, dating back to early days of quantum mechanics. While there have been challenges along the way, the potential implications of string theory are too significant to ignore. Who knows? It may hold the key to understanding the fundamental nature of the universe itself. At the heart of string theory is the idea that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional objects called strings. So what exactly is a string? Well, in physics, a string is a tiny, one-dimensional object that vibrates at different frequencies. Just like different musical notes are produced by different frequencies of sound waves. Different particles in the universe are produced by different frequencies of string vibrations. These strings are incredibly small, once again on the order of 10 to negative 33 centimeters. This is much smaller than any particle that we can currently observe with our most powerful microscopes. In fact, the strings are so tiny that they're thought to be the building blocks of all particles in the universe. But why strings? The idea of strings arose in the 1960s as a way to reconcile the main two theories of physics at the time, quantum physics and general relativity. These theories were incompatible with each other, and physicists were struggling to find a way to combine them into a single, unified theory. The idea of strings offered a way to do just that, by describing particles as tiny, vibrating strings instead of point-like particles. Physicists found that they could potentially unify all the fundamental forces in the universe, including gravity, electromagnetism, and the strong and weak nuclear forces. The idea of strings offered a way to do just that. By describing particles as tiny, vibrating strings instead of point-like particles, physicists found a way that they could potentially unify all the fundamental forces in the universe. Overall, strings are fundamental building blocks of the universe according to string theory. By vibrating at different frequencies, they can produce all the different particles that we observe in the universe. It's a radical idea, but one that could hold the key to understanding the fundamental nature of the universe itself. At its core, string theory is based on the idea that the fundamental building blocks of the universe are tiny, one-dimensional objects called strings. These strings vibrate at different frequencies, and these vibrations give rise to all the different particles and forces in the universe. But how does this actually work? Well, let's break it down. First, let's consider the concept of force. In classical physics, forces are described by fields. For example, the gravitational field describes the force of gravity between two masses. In string theory, forces are also described by fields, but these fields arise from the interactions between strings. When two strings come in contact with each other, they can exchange energy and information, which gives rise to different types of forces. For example, if two strings vibrate at just the same frequency, they can merge together and form a single or massive string. This process is known as string fusion, and it's thought to be responsible for the strong nuclear force that holds atomic nuclei together. Now let's consider the concept of particles. In classical physics, particles are point-like objects with no internal structure. In string theory, particles are not fundamental objects, but rather made up of strings vibrating at different specific frequencies. Different types of particles are produced by strings vibrating at different frequencies. For example, a photon, which is a particle of light, is produced by a string vibrating at a specific frequency. Similarly, an electron, which is the fundamental force of matter, is produced by a string vibrating at a different frequency. Overall, string theory provides a way to unify all the fundamental forces of the universe into a single, coherent framework. By describing particles as tiny vibrating strings, physicists were able to explain the behavior of the universe at the smallest scales. While there are still many unanswered questions and challenges associated with string theory, it remains one of the most exciting and promising areas of physics today. In addition to the concept of strings, another key aspect of string theory is that the idea that our universe has more than 3 dimensions, and one dimension of time that we're familiar with. In fact, string theory requires the existence of at least 10 dimensions, 9 of space and 1 of time. But how can this be? After all, we only seem to experience 3 dimensions of space in our everyday lives. The answer lies in the concept of compactification. In string theory, the extra dimensions are thought to be rolled up or compactified into incredibly small, curled up shapes. These shapes are so small that we cannot see or experience them directly, but they play a crucial role in the behavior of the universe at the smallest scales. One might think about compactification is to imagine an ant crawling on a telephone wire. From the ant's perspective, the wire looks like a one-dimensional line. The ant can only move forwards or backwards along the line, but from our perspective, we know that the wire actually has a second dimension. It also has width. Similarly, in string theory, the extra dimensions are hidden from our everyday experience, but they still have an impact on the behavior of particles and forces in the universe. In fact, the extra dimensions are thought to be the key to unifying all the fundamental forces of the universe, including gravity, electromagnetism, and the strong and weak nuclear forces. Overall, the concept of extra dimensions is a central aspect of string theory. By including these extra dimensions and understanding how they interact with strings and particles, physicists are able to describe the behavior of the universe at the smallest scales. While it's a challenging concept to wrap our heads around, it's also an incredibly exciting one. After all, it could hold the key to understanding the true nature of the universe itself. String theory is an incredibly exciting area of physics with far-reaching implications for the understanding of our universe. Here are some of the key implications of string theory. One of the main goals of string theory is to unify all the fundamental forces of nature into a single, coherent framework. For example, some physicists have speculated that the extra dimensions could provide a hiding place for dark matter, a mysterious substance that makes up most of the matter in the universe. But which we have yet to detect directly. For example, some physicists have speculated that the extra dimensions provide a hiding place for dark matter, a mysterious substance that makes up most of the universe, but which we've yet to detect directly. 3. Black holes. Another intriguing implication of string theory is its potential impact on our understanding of black holes, the ultra-dense objects formed when massive stars collapse. According to string theory, black holes could be fuzzballs, incredibly complex, tangled webs of strings that exist at the event horizon of the black hole. This is a radical departure from the classical understanding of black holes as simple, smooth objects with no internal structure. If string theory is correct, then black holes could be even more fascinating and mysterious than we've ever imagined. 4. Multiverse. Finally, one of the most mind-bending implications of string theory is the possibility of a multiverse, a vast, possibly infinite collection of universes that exist alongside our own. This idea arises from the fact that string theory allows a huge number of possible configurations of the extra dimensions. Some physicists have speculated that each of these configurations could correspond to a different universe, each with its own laws of physics and unique characteristics. This idea is still highly speculative, but it underscores the profound implications of string theory for our understanding of the universe. Overall, string theory is a rich and fascinating area of physics with far-reaching implications for understanding the universe. While there are still many unanswered questions and challenges along with string theory, it remains one of the most exciting and promising areas of physics today. Well, string theory is an exciting area of physics with many potential implications for the understanding of our universe. It also faces a number of challenges and open questions. Here are some of the main challenges of string theory. Lack of experimental evidence. One of the biggest challenges facing string theory today is the lack of experimental evidence. Since string theory deals with incredibly small scales and energies, it's extremely difficult to test the theory through experimentation. As a result, many critics argue that string theory is not a scientific theory at all, since it cannot be tested through experimentation. 2. Complexity. Another challenge of string theory is its incredible complexity. The theory requires the existence of extra dimensions, involves a vast array of mathematical concepts and techniques. This can make the theory difficult to understand and work with, even for experienced physicists. 3. Lack of predictive power. Another criticism of string theory is that it lacks predictive power. That is, it cannot make specific, testable predictions about the behavior of a universe that differ from the predictions of other theories. This makes it difficult to determine whether the theory is correct, since it cannot be directly tested through experimentation. 4. The landscape problem. Finally, one of the most controversial challenges facing string theory is the landscape problem. This problem arises from the fact that string theory allows a huge number of possible configurations of the extra dimensions in the universe, far more than the number of possible universes that we observe in our own universe. This has led some physicists to question whether string theory can provide a unique, testable theory of the universe, or whether it simply leads to a vast number of different universes with different laws of physics. This has led to an intense debate within the physics community and remains one of the most controversial and challenging aspects of string theory. Overall, while string theory holds tremendous promise for our understanding of the universe, it also faces a number of challenges and open questions. As physicists continue to explore and refine the theory, it's likely that some of these challenges will be overcome, but others may continue to pose significant obstacles to our understanding of the universe. Despite the challenges facing string theory, many physicists believe that the theory holds tremendous promise for our understanding of the universe. Here are some of the potential directions for the future of string theory. 1. Further mathematical developments. One potential direction for the future of string theory is further mathematical development. String theory requires a vast array of mathematical concepts and techniques, and some physicists believe that a deeper understanding of these mathematical structures, new insights and predictions about the behavior of the universe. 2. New experimental evidence. Another potential direction of string theory is the possibility of new experimental evidence. While it's currently very difficult to test string theory through experiments, new technologies and techniques will eventually make it possible to detect the effects of extra dimensions or other predictions of the theory. 3. Alternative theories. Finally, another potential direction for the future of string theory is the development of alternative theories. While string theory is currently one of the most popular and well-known theories of the universe, there are other competing theories that could potentially explain the behavior of the universe without requiring extra dimensions or the other concepts of string theory. Overall, the future of string theory is uncertain, but it remains an active area of research and study for physicists around the world. As new discoveries are made and new technologies are developed, it's likely that we'll gain a deeper understanding of the theory and the universe itself. In conclusion, string theory remains a fascinating and complex area of physics that holds tremendous promise for understanding the universe. While the theory faces a number of open challenges, and questions, it also offers new insights and potential solutions to some of the most fundamental problems in physics. By proposing that the fundamental building blocks in the universe are tiny, one-dimensional strings vibrating in higher dimensional space, string theory offers a radically different perspective on the nature of reality. And while the theory may seem far-fetched, or even unprovable to some, it remains an active area of research and study for physicists around the world. Whether string theory ultimately proves to be correct or not, it represents an important step forward in our ongoing quest to understand the nature of the universe. By challenging our assumptions and expanding our thinking, string theory reminds us of the power and the beauty of science, and of the limitless potential of the human mind to explore the mysteries of the universe. Thank you so much for watching this YouTube video. If you liked it, please give a like, and if you'd like to see more videos like this, please consider subscribing. Thank you.